Good afternoon, everyone. I would like to welcome you to the breakout panel focused on the important topic of climate change and water resources. My name is Eva Holupchinski, coordinator of the Caribbean Climate Hub, and I have the pleasure of moderating today's session. We will have in the next 40 minutes, you will hear from a wonderful group of experts about Caribbean water resources in the context of climate change projections, drought, and water resource monitoring. First, we will hear from Jared Bowden, Senior Research Scholar at North Carolina State University, Greg Ramseyer, Assistant Professor at Virginia Tech Department of Geography, David Sumner, Director of the USGS Caribbean Florida Water Science Center, and Odalys Martinez, Hydro-meteorologist at NOAA-National Weather Service. Without further ado, let's get started with Jared Bowden.
Thanks for inviting me to this conference. It's a really nice conference, and thinking about interagency and how interagencies can work together is very important. And actually, part of this work was related to an interagency agreement between USGS and US EPA. And it was initiated by USGS. And I have to thank my colleagues at USGS, including Adam Tarando and Ryan Bowles, my colleagues at NC State, Jaime Collazo, and then also some colleagues at EPA, in particular, Tanya Spiro, that helped think about some of these problems related to developing climate change projections for the islands. And so today I'm going to talk quickly about some downscaled high resolution climate change projections with an emphasis on Puerto Rico. These projections are at a resolution of about 2 kilometers, and they produce hourly output for mid-century projections. In particular, that was our focus given our application on ecosystems from the initial stages of this project. So you can't really talk about the complexity of climate change from a regional perspective without thinking about the big picture. And I just want to, policy is very important for the Caribbean, and there's always this push that the islands are very sensitive to climate change. In particular, this is looking at a very aggressive high greenhouse gas emission scenario out towards the end of century, which as you probably saw this with Adam, but it's becoming more and more unlikely that this would be the path we're taking given current trends and our path to curb emissions. But if we do go this case, it's a very dire situation for the entire planet, and the mean global temperatures, when you think about the scenario, in about 3 times the amount of CO2 increase compared to today would equate to about a global mean increase in temperatures of 4.5 degrees Celsius on average. And that's a significant burden to think about. But if you go specifically and you think about the islands and you think about, well, what may happen in the islands, one thing that's very obvious, and if you look at the mid-century on the left-hand side is for middle of the road greenhouse gas emission scenario where we curb emissions around 2050 and they start to drop after that point. And then you go on the right-hand side into a more aggressive greenhouse gas emission scenario. And we keep thinking about, well, what does policy mean if we don't curb these emissions? It's very obvious that at end of century, thinking about those two, you're going to have very large differences in the amount of temperature increase locally for the islands. But the problem is that these global climate models don't really see the islands. And so if you really look at this, the picture here, I said islands changes are similar to the ocean. And it's just because basically, what do they see? They see basically ocean and don't really see land, especially when you start thinking about the USVI. Now, if you go to high resolution climate change projections, one of the things that I want to take away is what can we learn from the high resolution climate change projections that we do have available to us? And they're very limited. They're very expensive to calculate. They take on the order of using 100 plus processors to do these simulations just for a 20-year mid-century period to look at changes in the future relative to a baseline of 20 years. it takes over a year to calculate running continuous simulations on hundreds of processors. And so this is a very computationally intensive, and that's why you don't really see a lot of this in the literature and helping us understand what's going to happen. But well, what can these model projections tell us? And if you take a look at this picture here, you'll see that the island temperatures, especially for the maximum temperatures, are basically much warmer than the background ocean. And what you're really seeing from the global climate models is the ocean picture. And so, and you'll see the complexity within the island itself. For instance, I highlighted in blue, like El Yunque, you really see that there's a less fingerprint of warming for there relative maybe portions of other parts of the island. And I highlighted that area in black there to represent some of the largest increases. And the reason why those places are increasing so much is the models also simulate that the annual rainfall deficit declines more in that region relative to other places. And actually, there's very important land surface feedbacks that happen that cause that localized warming. And so the big picture is that as you move to higher resolution, that we may be really not seeing the big picture of how much warming we may get, especially in a climate that we may anticipate some drying in the future. So the key message for temperature is that policy is very important, and the GCMs depict greater than 1 degree C differences in mean warming by end of century. And so for that SSP 2 4.5, which is the middle of the road scenario, where you basically try to think about emission reductions, trying to get to 2050 and then reducing, leaves us under 2 degrees C locally, where if you go to the, by end of century, where if you go to the higher emission scenario, you have much larger temperatures of greater than 3 degrees C, which would mean relatively large impacts locally. Now, the problem is with the global climate models, you underestimate the magnitude of warming because they don't resolve these islands. And these regional climate model projections that I'm showing here resolve complex land use and terrain, and basically indicate that there's likely going to be much warmer temperatures than the background ocean. And locally, this could be much larger within the island, and it's related to the land surface feedbacks, in particular during the maximum temperatures during the day, when you don't basically, when things start to dry up a little bit within the island, all of that energy goes into heating the surface than evaporation. And so you get much larger temperature increases. And I'll show some of the precip in a minute. Now, for policy, thinking about the big picture of what's happening, what could possibly happen in the future with precipitation is there's a large sensitivity in this region to how much drying is possible in the future climate as greenhouse gases continue to increase. And this is really related to, and if you look at globally, where are all these browns that you see, which are basically the drying, these are over subtropical oceans. And in particular in the North Atlantic, the North Atlantic subtropical high or Bermuda high, this is the area where we're seeing a large changes in how much precipitation reductions you have. And this really equates to timing of the year based on what the GCMC and in particular during the summertime when the Bermuda high is maybe a little bit stronger, and you'll see larger reductions during that period of time. And that's what I'm showing in that time series that you see below the global picture is that brown is really a time from May to like October where you're seeing large reductions in precipitation based on the global climate models. If you take a look at this from a policy perspective from the global climate models, and you think about what happens around mid-century towards end of century, on the top left is like the lower mid-century changes of like 7% to, you don't really see much differences by end of century for that same scenario if you reduce emissions. But if you go to the end of century and you don't reduce them, you see that this is where policy becomes very important. You have upwards of 27% reductions. And so based on the global climate models, and this is the most latest climate models that we have available through CMIP-6. If you think about the islands in particular, and you look at downscale precipitation at mid-century for one of the higher greenhouse gas emission scenarios, there's a couple things to take away that the global climate models may not see. In particular, localized changes in terms of the reduction amount, in terms of precipitation, may be much larger than what the GCM suggests. But we don't anticipate this to be uniform within the island. And there is a sensitivity that we've seen in many of our simulations that the higher terrain, which is the elevations I show you in contours here, this is the model elevation in particular. And you see the blue that I have in the wet season, and some of these higher elevations, actually you see slightly an increase in precipitation. And so you don't anticipate basically same reductions within the island, but this may be an opportunity to think about higher elevations may actually help to buffer the large scale drying that we may see. And then finally, I'd like to say that both the dry and the wet season do see reductions within the island, unlike what the global climate models we saw for the end of century are suggesting. And so there's a complexity in terms of what will happen in terms of seasonality based on what the climate high resolution climate models suggest. So the key message for precipitation is the GCMs indicate a large sensitivity in the annual rainfall reduction across the entire Caribbean, and basically higher greenhouse gas emission scenarios equate to larger rainfall reductions, especially during the wet season. But the global climate models really underestimate the complexity of the regional impacts when considering rainfall reductions. And in some of the lessons learned that we're seeing here is that based on the few realizations of the climate at these scales, these higher scales that can resolve the islands, is that the rainfall reductions may be larger than what the global climate model suggests, just similar to temperature. And in that you may have actual reductions throughout the entire year and not focus just primarily during the wet season as what the global climate models were suggesting. There is an elevational sensitivity in the magnitude of the rainfall reductions. And this is somewhat related to local recycling of water and having forest cover at those altitudes, and the models being able to see that forest and being able to take advantage of that local recycling of water, and something that's probably going to be very important. And then one of the things that I think to take away from this is that the results imply plausible adaptation measures within eastern Puerto Rico when considering the availability of water, especially when you think about the elevational sensitivity. And so I think that's pretty important to think about what these sensitivities or these model simulations kind of indicate.
Jared, just to know that we're at the time, so if you can go ahead and wrap it up, that would be great.
Yeah, this is my last slide. And so I'd like to just say that the main message, the main takeaway is there is an increasing risk of aridity directly as a result of both increasing temperature and rainfall reductions. And what I'm showing you here is relative changes in the model soil moisture. So this is really the top 10 centimeters of soil during the wet season. And that blue is where you saw increases before. But now when you look at the actual soil, the rainfall increases, but the evaporation demand is larger. So you get ultimately a drying out of the surface, which I think is very important for many downstream impacts. So I'll stop there and thank you for having me.
Now I would like to introduce Craig Ramseyer, Assistant Professor at Virginia Tech Department of Geography.
Well, thank you. And thanks to Jared. He gave me a really nice introduction to the topic I'll be discussing here, which I've termed broadly understanding drought mechanisms in the Caribbean. And although I'm presenting, there's a whole team of folks that have been involved with the research I'll present, and they're listed on the slide. And really, this will be a synthesis of two projects we have ongoing, one funded by the NOAA MAP project and the other by the Luquillo LTER project. And I'm going to kind of cover three things as quickly as possible here. And the first will be looking at some past research we've done, just trying to understand the large-scale forcing mechanisms that drive sort of what we're going to call traditional meteorological drought. These are droughts that can evolve over the time scale of months, sort of long-term drought. Then I'll introduce sort of some new work we're doing with a new drought index called the EDDI. And we think it shows some promise in being a potential early alert for impending drought. And then the last thing I want to discuss is some really new research that's just evolved over the last month or so, where we're starting to try to diagnose flash drought in the Caribbean. So quickly, the sort of overview of some of the drought forcings we've already acknowledged. Some of them are pretty obvious, such as sort of lower than expected moisture. We've published on looking at the relationship between wind shear and rainfall, and we find that with positive wind shear, it's more difficult to get coherent thunderstorm structures, and thus lowers rainfall. And we've also played around with a convective index called the Galvez-Davison index, which is sort of a thunderstorm index that's been tuned or developed specifically for the tropics. And we show that when the index becomes more negative than usual and GDI is lower than what we would expect, we see lower rainfall, particularly during the early rainfall season, which is interesting because in Jared's talk, we can see that that's when we see future projections for lower rainfall kind of reach their peaks. So we're doing a lot of work with that. A couple of other drought mechanisms we've published on is the trade wind inversion. And again, trade wind inversions, when stronger than expected, can cap thunderstorm development and thus lower rainfall. And our paper shows that there are some interesting potential trends out there with the trade wind inversion that we can observe over the last 40 years, suggesting maybe trade wind inversions are growing slightly more stronger than expected. And then we've also looked at the Saharan air layer and dust, and we show that during the early rainfall season in particular, that those are sort of drivers of lower rainfall. And so we've got some ongoing research with the trade wind inversion and the Saharan air layer, trying to understand those complexities and how they may be interacting with one another. But I want to I think for this particular audience, talking about some of the newer research we're doing maybe of most interest, one of which is using the evaporative demand drought index to look at Caribbean drought. And we've also, I'm just going to present on sort of Caribbean broadly here, but we're also doing some work on Puerto Rico specifically. And I'm not going to scare you with what's going on here, but I just wanted to kind of highlight why the EDDI is kind of a promising new drought index, especially for trying to detect drought very early on in the process. Basically, EDDI is trying to get at drought before we see it observed in sort of rainfall reductions, before it's observed in soil moisture anomalies. And really what EDDI is trying to do is to understand how thirsty the atmosphere is for moisture. And so EDDI uses wind speed and radiation, all the stuff you see on the slide, and then basically understands, is it more or less thirsty than we'd expect given the time of year. So there is sort of a climatological component to EDDI as well. So you'll see in the next slide, the scale on the map in the top ranges from negative to positive values. Positive, I've shaded brown here for you, and that indicates high EDDI, or again, thirstier than normal conditions. And this again is going to promote lots of evaporation and transfer of moisture out of the land surface and up into the atmosphere. And so EDDI, what I'm showing on this slide is looking at patterns of EDDI that we've observed over the last 41 years using a machine learning model. And so we see like different patterns that can evolve with EDDI. And one I've highlighted here in the red box is one particular kind of EDDI setup that we can observe where there's really sort of Caribbean-wide drying denoted, and there's not a lot of green on that map at all. And so it's kind of interest because of this sort of broad Caribbean drying signal. It says increasing in that particular box because statistically significantly speaking, the frequency that this type of setup in EDDI has been observed over the last 40 years is actually increasing. And you can see that on the bottom in this particular histogram, that in the 80s, this sort of Caribbean-wide drying type signal wasn't observed much. And you can see here in the last decade, obviously, a much more common kind of EDDI signal that we observe. You'll also note for those climate folks in the audience, the 97-98 El Nino kind of shows up kind of nicely as well, denoting sort of Caribbean-wide drying as well. And the last thing I want to touch on here, and I can answer any questions at the end when everybody wraps up. But I want to talk about flash drought too. And so flash drought is sort of a newer concept in the literature, maybe a decade or so old, kind of trying to isolate drought events that occur very rapidly. And so the onset of drought happens on the time scale of days to weeks instead of months. And these particular types of drought can be very impactful, especially for stakeholders. So in the Caribbean, flash drought's not been discussed a ton. And so we're investigating, pretty simple questions about, does flash drought actually occur, or what does it look like in the Caribbean? And there's a lot of different definitions for flash drought. Folks have proposed looking at soil moisture depletion rates. How quickly does the soil moisture deplete? There's a bunch of satellite-based metrics that have been proposed, but one that we like, because again, we're trying to think about how do we predict drought, especially ones that evolve very rapidly. And we have the EDDI data available. We've calculated it for the entire Caribbean. So we're going to use this new flash drought definition that's been in the literature only for about 2 years, where we're looking at changes in EDDI. And so you'll see the definition we're using here is a 50% increase in EDDI. That has to occur within 15 days. So this is a rapid increase in EDDI, again, representing a really rapid increase in how thirsty the atmosphere is, driving again, promoting a lot of evaporation, and then that must sustain itself for 15 days. So that's a lot of words. Let's look at what EDDI kind of looks like in reality. So here I've just extracted one example of a flash drought that meets this criteria. For those of you that are familiar with that latitude, longitude, that's in eastern Puerto Rico. That's a grid point awfully near El Yunque, where a flash drought was detected in our data set. And you can see here that on the left-hand panel, so we're starting in mid-December and we're just ending in mid-January here. This particular grid point shows really low EDDI at the beginning of a flash drought, right? Within 5 days, you can see it going from about negative 1.7, jumping up to about 0.7. So that again is well beyond that 50% threshold that we talked about. And that's happening within about a 5 to 7 day period. Again, hinting at how rapid drought conditions can evolve at somewhere like Puerto Rico. And then you'll see over the next month or so, EDDI sort of slowly ticks up, but it certainly sustains that initial jump of 0.7 and sort of hinting at this sustained, really thirsty atmosphere that's again going to try to tap into all that moisture that is on the land surface. And so one of the reasons I show this is because it's in Puerto Rico. The other reason because this happens mid-December of 2014. We are starting to look into whether or not this was actually the initiation point for the 2015 Puerto Rico drought, which we've also published on. The last thing I want to show you real quickly here is we're also trying to understand why flash droughts occur, like kind of what are the forcing mechanisms in the atmosphere causing flash drought. And here's sort of another machine learning model we've run to try to understand how vertical motion in the atmosphere looks into 12 groups, again, over 40 years of data. On the top row, you see blues. That means upward motion. On the bottom row, you see lots of red. That indicates the atmosphere sort of sinking at a large scale. At initiation point, most of our flash droughts that happen in Puerto Rico, which is what these numbers are kind of representing, a lot of times they initiate in regimes where there is a lot of upward motion. There's a lot of cloud cover, maybe. There's even precipitation occurring, and that's going to set the EDDI rather low. All right. Over days 6 to 10 look like this. You'll see the numbers dropping on the top row. And slowly, as I go through these next couple slides, you'll see the numbers on the bottom row start to really increase, suggesting that at initiation, we may have upward motion, but really it's this sinking motions over the Eastern Caribbean that are really driving that flash drought, right? It's really sort of promoting a lot of sinking motions that are drying out the atmosphere. By days 16 to 20. Okay.
Excuse me, just want to note that your time is concluding. So if you could go ahead and wrap up, that would be great. Thank you.
By days 16 to 20, you see almost all flash droughts are sort of punctuated with this large scale sinking motions in the atmosphere. So we think that there's something here. We're going to start trying to figure out what's forcing that sinking motion. Is it sort of an expansion of the Bermuda High or Saharan air layer or some combination? And instead of talking about conclusions, we can come back to these. So thank you for your time, and look forward to questions later. Thank you.
Excellent. Thank you so much, Craig, for your presentation. Now we will shift to David Sumner, Director of the USGS Caribbean Florida Water Science Center. Excellent.
Hello, everyone. Dave Sumner here. I'd like to talk a bit about monitoring freshwater resources in the Caribbean. You're probably all familiar with the food, water, energy nexus, and of course, there's a critical component of that nexus that's required to be healthy for sustainability of us humans. The Anthropocene has been proposed as a geologic epoch that represents the current time where humans have an impactful and profound effect on the planet. And we've talked a bit today about climate change and its genesis and burning of fossil fuels. The Anthropocene also has some other human impacts that are really profound as well, that are going to impact the hydrosphere. So landscape changes have been massive, and also the generation of all the chemicals that we do generate as humans and their entry into the environment. And just to put things in context, I thought this was interesting. The beginning of the Anthropocene has been disputed, but I would argue it's in 1950, based on these figures here. You see that the world population, the GDP of the world, our energy usage, construction of large dams, water use, expansion, use of fertilizers, all seems to inflect at this red year on the x-axis, which is 1950. And that has been called the Great Acceleration. So in the last 70 years, we've really geared it up, and we've created what you might call the good life on planet Earth for a lot of folks. But there are impacts to the good life. There are costs to the good life. And you can see in this figure, carbon dioxide also is inflected up in 1950. Methane, ozone, surface temperature, ocean acidification, fish populations, species diversity, and coastal nitrogen have all picked up as well and inflected in 1950. So that seems to be a critical time. We're really accelerating our impact on the planet. Now, the USGS Caribbean Florida Water Science Center is trying to look at, as I said, the water resources of Puerto Rico and the Virgin Islands, the US Caribbean. And these numbers on the left include Florida as well, which is part of our domain. But I would say that Puerto Rico has the most dense USGS hydrologic monitoring of the entire nation, if you compute it on a per square mile basis. The US Virgin Islands less so. We need to do some work there. But we measure, as you can see here, stream discharge, stream water quality, groundwater levels, precipitation, reservoir capacity, which is diminishing because of sedimentation, saltwater front mapping, evapotranspiration, a huge part of the water budget, solar radiation, a term that, or a parameter that's often not looked at in climate change. I would argue it should be, because cloud cover is also changing with climate change, impacts solar, which impacts biological productivity and evapotranspiration and surface temperature, and a whole range of other things. And then we try to, I think this data that we collect in the USGS is very important because it can be assimilated into hydrologic models, climate models, to really provide integrity to those models. And those models, of course, the added feature that we heard from Jared's talk earlier is that they have the ability to project into the future and allow us to plan. I'm just going to go through some of the ways we measure in the hydrosphere in Puerto Rico and the Virgin Islands. These are some images of stream flow measurement. We use hydroacoustic approaches, and you can see in the middle slide, the stream at low water, and that same stream at high water on the far right. We take measurements every 8 weeks or so of the discharge, and then we use that data along with continuous levels of the stream that we measure, as I said, continuously with a deployed station to infer continuous discharge. This is important for water supply and for flooding reaction time. We also have a huge program in measuring the water levels in the aquifers in Puerto Rico and the Virgin Islands, in fact. This image is on the south coast of Puerto Rico. You probably are all familiar with the South Coast Aquifer. It's a stretched aquifer in the sense that there are a lot of competing interest in pumping water from that aquifer, and it's stressed in terms of that's the dry side of the island, and the ocean is not too far away, and so there is the risk of saltwater intrusion. But we take these measurements that are used to react to droughts, to foresee the trends that are developing in terms of lost groundwater resources, possible salinization of the aquifer. We also—
Hi, Dave. I'm sorry to interrupt. Just letting you know you've got 3 minutes remaining.
Okay. We also measure water quality continuously in the island, various parameters. We take discrete water samples as well, that those we can send to a laboratory to measure a whole range of water quality constituents. We react to storms, and this is a fellow making a high water measurement after Hurricane Maria, and shows the extent of the water, water surge, which guides hazard mapping in Puerto Rico. We also measure continuously the time series of storm surge, which informs storm surge models, makes those models better. We measure water use, and we have a study going on in the Virgin Islands where we're monitoring water use in 18 farms, and that monitoring should help identify the need of agriculture in the Virgin Islands, allowing the authorities in the Virgin Islands to prepare the infrastructure to meet that need. We're also involved in projection of water use into the future, estimates of that based on climate change, drought, or changing crops. We monitor greenhouse gases as they interact between the landscape and the atmosphere, both water, which is a greenhouse gas, evapotranspiration, CO2, methane, and that really, as you might imagine, there is an interaction between transpiration and biological productivity, carbon sequestration. We can quantify that. You can see the image here of an inundated street. This happens to be in Miami Beach, but we have this problem around the Caribbean as well. Inundation due to rising sea level, which is a consequence of climate change. In Florida and Puerto Rico and the Virgin Islands, I think rising sea levels could also cause increased salinization of our aquifers. Key messages: the freshwater resources are under multiple threats during this period of the Anthropocene, the current period, and hydrologic monitoring of the freshwater resources can inform water resource management in pursuit of resiliency in the face of climate change. So I'll stop there. Thanks.
Thank you, Eva. Thank you for having me. Buenas tardes. Mi nombre es Odalys Martínez, en el Servicio Nacional de Meteorología, siempre a la orden. En esta presentación tengo dos objetivos. Me gustaría mostrarles las tendencias observadas en nuestras estaciones meteorológicas alrededor de la isla. De igual manera, compartir con ustedes lo que hemos aprendido en la oficina a través de los años, las preguntas que han surgido a través de los años, particularmente trabajando con cambio climático y los manejadores del recurso agua. Para comenzar con las tendencias observadas en las estaciones del Servicio Nacional de Meteorología, nosotros tenemos aproximadamente de 60 a 70 estaciones a través de Puerto Rico e Islas Vírgenes, Algunas reportan lluvia, otras temperatura, otras lluvia y temperatura. Estas, como mencioné, están entre Puerto Rico e Islas Vírgenes. Las que se utilizaron para el análisis de tendencias son aquellas estaciones que tienen el periodo de récord más largo y robusto. Son estaciones centenarias y en su mayoría, por no decir que todas, están realmente en Puerto Rico. Lo que sería esas estaciones centenarias en Islas Vírgenes, la data es un poco más limitada. Estas estaciones forman parte del network global de climatología histórica. Cuando nosotros hablamos, ¿verdad?, de todo lo que serían estas tendencias observadas y el manejo del recurso agua, muchas veces es más fácil asociar con los patrones de lluvia, pero en realidad es bien importante de igual manera entender qué es lo que está sucediendo con la temperatura. Y el detalle se encuentra en que tienes obviamente evaporación, pero de igual manera tienes una población allá afuera que busca refrescarse y no necesariamente va a estar limitado precisamente al aire acondicionado. Así que lo más seguro vamos a poder entonces estar observando en esos periodos un incremento en el consumo de agua que a su vez pone presión en los abastos de agua. Como bien mencionó ayer el doctor Adam Terando, la temperatura en Puerto Rico ha aumentado al menos 2 grados Fahrenheit desde el 1950. Si nos vamos al detalle, al número de días con temperaturas máximas sobre los 95 grados, que es la imagen de la izquierda, y las noches con temperaturas sobre los 80 grados, que es la imagen de la derecha, al momento no se encuentra una tendencia, no se ha visto ni un aumento ni una disminución en el número de días con temperaturas sobre los 95 grados. Pero sí se ha observado que las noches con temperatura de 80 grados o más han aumentado. Así que esto significa que no nos estamos enfriando. Y es muy válida la pregunta de hay una población allá afuera que busca refrescarse, busca enfriarse y otra vez. No necesariamente va a ser limitado al aire acondicionado. Esto puede estar ejerciendo una presión en el consumo de agua, de igual manera en los abastos de agua de la isla. En términos de lo que sería la precipitación anual, la lluvia anual en la zona de Puerto Rico, de igual manera, como mencionó muy bien ayer el doctor Adam Terando, no se ve ningún tipo de patrón desde el 1950 al presente. Eso sí, se ha visto que la lluvia anual desde el 1903 ha estado cercano o por encima de lo que sería promedio. Y uno se pregunta, pero ven acá, ¿cómo esto es posible? Cuando precisamente hemos estado en tiempos recientes viendo episodios de sequía. Vimos el del 2015, de igual manera en el 2020. Así que la pregunta es muy válida, ¿qué es lo que está sucediendo? La explicación podría estar precisamente en ver esos totales anuales de lluvia cercano o por encima de lo que sería normal, dado la precipitación extrema, esos días en donde vemos totales de lluvia por encima de las 3 pulgadas. Ciertamente la data muestra que desde 1950 al presente, ese número de días con lluvia sobre 3 pulgadas no ha aumentado, pero contribuye a ese total anual de lluvia. Y es muy importante mencionar, cuando estamos precisamente trabajando con cambio climático y cómo se maneja el recurso de agua en la isla, que no necesariamente hay que verlo desde el total de lluvia anual. Es mejor verlo como lo que es un patrón bimodal, en donde tenemos el primer pico de lluvia aproximadamente en mayo, seguido de un segundo pico de lluvia en agosto, septiembre y octubre. El mejor ejemplo, la mejor manera de ver esto, podemos empezar un año totalmente normal con todos nuestros embalses en buenas condiciones, con todos los caudales de río en buenas condiciones, y entonces vemos que en enero, febrero y marzo empiezan a descender esos caudales, empiezan a descender esos niveles, lo que es normal porque son meses relativamente secos. Claro está, esperamos siempre las lluvias de mayo. Las lluvias de mayo son las lluvias que recargan esos abastos, son esas lluvias que recargan esos caudales. De esas lluvias no llegar, nos movemos a junio, julio, que son meses relativamente secos si lo comparamos con mayo y con agosto. Así que esa tendencia a disminuir continúa. Si a eso se le añade el detalle de que tal vez tengamos un verano peculiarmente caliente, como lo fue en el 2012, donde los días sobre 90 grados fueron aproximadamente más de 30 o 35 consecutivos, nuevamente vas a tener una población ahí que va a querer refrescarse y está ejerciendo presión adicional precisamente a esos abastos de agua. Así que es bien importante, como mencionaron los compañeros panelistas, precisamente entender ese patrón bimodal de lluvia, donde si ese patrón está cambiando, si esos picos de lluvia están cambiando, se están eliminando, para poder entonces así explicarle esto a nuestros manejadores del recurso agua, ya que ellos siempre, ¿verdad?, esperan ese primer pico de lluvia en mayo, porque son las que recargan nuestros acuíferos, nuestros ríos, nuestros lagos.
Permiso.
Lo que quiero que se lleven de esta presentación es, ciertamente las temperaturas están aumentando a través de Puerto Rico, especialmente, ¿verdad? Se sienten más esas noches cálidas, no nos estamos enfriando, así que hay que tener en mente, siempre se tiene que considerar que la gente quiere enfriarse, no necesariamente con el aire acondicionado. Siempre se menciona que es una cuestión de que va a aumentar el consumo energético, sí, cierto, pero de igual manera puede ejercer una presión en nuestros abastos de agua. Y al momento la literatura menciona, no hemos visto del 1950 al presente patrones en el cambio de lluvia, y sí a futuro veremos una reducción en precipitación, pero lo que estamos viendo ahora también tenemos que entenderlo, y la realidad probablemente sea, como mencionó de los compañeros panelistas, flash drought. Estamos viendo que entre evento y evento de lluvia, que son lo suficientemente vigorosos para que recarguen los acuíferos, para que recarguen los lagos, se está tardando. Y en ese proceso es a donde empezamos a ver los impactos en el suelo, en los agricultores y en los abastos de agua. Muchas gracias.
Excellent. Thank you, Odalys, for your wonderful presentation. And now we will pass to the question and answers session. So this is a question for all panelists. What research is needed to support decision makers in the management and protection of water resources on the islands? And we can start with Jared Bowden.
Yeah, that's a loaded question to some degree, but you know, when I think about from a modeling perspective, one of the things that's very challenging for the islands is having observations, and I think observing how the climate is changing at these scales is critically important. And so, you know, from a modeling perspective, you know, I always think about how the models are doing in the future, but if I can't evaluate how well my models are doing from a historical perspective, that's also a challenge. And so I'm big about modeling and thinking about the future and what the future may hold. But I think when it comes down to everything, I think really thinking about the observational network within the island and improving that and being able to talk about things like flash drought and being able to pick up if it is soil moisture related, then that means we need a really good network to monitor that within the island. So I'll let somebody else chime in behind me.
Thank you, Jared. Do any other panelists have a comment?
Totalmente de acuerdo con Jared. Es muy importante entender el detalle de cómo estamos cambiando desde la perspectiva de la oficina, que trabajamos mucho con manejadores de emergencia, con los manejadores del recurso agua. Es importante entender esos cambios que se esperan, así que ese modelaje tiene que ser lo mejor posible, porque como mencioné, ellos, de la manera que se trabaja el recurso agua, está atado precisamente a ese patrón bimodal. Siempre esperan esas lluvias de mayo, y si hay algún tipo de cambio con ese primer pico de lluvia en la zona, pues definitivamente se tiene que entender para poder entonces ajustar cómo se maneja el recurso.
Thank you, Odalys. I see we have a question in the chat. If climate change models predicting drought for the Caribbean, what specific actions are being taken for conserving water in Puerto Rico and the Virgin Islands? Reforestation, protecting riparian zones, removal of sediments, or others? Would anyone like to comment on this question?
Por lo menos desde la perspectiva de, nuevamente, manejadores de emergencia, manejadores del recurso de agua, ellos al momento entiendo que están más, el awareness ha aumentado. Así que siempre están bien pendientes de esos déficits de lluvia que están ocurriendo, reportes del field, de igual manera cuál es el pronóstico por los próximos 3, 4, 5 meses. Así que al menos desde la perspectiva del manejador de agua, eso es el cambio que yo he visto en los últimos años.
This question is specifically for Craig, perhaps. You mentioned widespread drying in the Caribbean, though it seems that observed rainfall data seems to indicate an overall increase in rainfall within the last 30 years. Do you have any thoughts on why this might be?
Yeah, that's always a great question. Yeah, so I think when you, at least in the research we've done, it seems that when you look at annual rainfall, and Odalys showed a figure that showed that really well, there's a lot of interannual variability and there's no, real coherent trend. When you start drilling down though, and looking at sort of sub-annual timescales, looking at, for example, the early rainfall season, some of our research has shown the early rainfall season from April to July appears to be a little bit more sensitive to the changing climate than perhaps the late rainfall season, where, Puerto Rico, for example, can make up rainfall really quickly starting in August and September. If they get several tropical waves, tropical cyclone passes nearby, you can accumulate rainfall really quickly to make up deficits. But in the dry season, in the early rainfall season, you can have pronounced sort of drying, but also make up for a lot of those losses in a late rainfall season. So we think tends to be what happens. And I think one of the things Jared showed that was really interesting to me, I hadn't seen a figure like that before, showing where the models tend to be concentrating a lot of the rainfall reductions are also in that early rainfall season, April, May, June period. And so our research group is really interested in, is there sort of an elongation of the dry season that's going to start occurring, where you get sort of, instead of the dry season ending in March, April, does that get pushed back into June, July? And that's obviously really concerning, as Odalys laid out, with recharging aquifers and reservoirs. So we think that's what's happening. Again, that's just based on our research, but that's a great question.
Thank you, Craig. I see a question in the chat. Question for Jared and others. It seems like observations show that minimum temperature increasing more than maximum temperature historically, but I think projections show the maximum temperature increasing more than T minimum in the future, excuse me. What explains this difference?
Yeah, that's a good question. So the big picture is that what we haven't realized yet in this current state of the climate is this annual rainfall reduction being persistent. If that happens, and as the models indicate under this one emission pathway, if that happens to happen, what ends up happening is there's a feedback in the climate system, and so the soils start to dry out. And so once the soils start to dry out, the big thing is where does the energy go? It doesn't go into evaporation anymore. It goes into what we call sensible heat. And so you go into heating the surface. And so that's the big problem is that once you start to dry things out, and if it's persistently drier from year to year to year to year, then where does that energy go? It goes into during the daytime, and that's why the daytime maximum temperatures start to increase faster. And so that's why I think observations are very important, because if you start seeing this flipping of the observational record saying Tmax is now increasing, and if that tends to happen, I think that's a signature that you're going into a different state of the climate.
Excellent. Thank you, Jared. A question for David and Odalys. Many farmers I work with in the south of Puerto Rico are interested in having data on hand about the levels of their farm's wells, which take water from the aquifer, and are also interested in neighborhood-specific data on precipitation projections. Is there any tool that provides this data? Is there an upcoming project or opportunity to address that? David or Odalys, would you like to respond?
Yeah, I'll jump in on the first part, maybe Odalys, precipitation question. But yes, NWIS Mapper, NWIS Mapper, 2 words. That's a USGS tool that you can go in and see real-time data on water levels, wherever we might have those in Puerto Rico. So those are, our stations are autonomous. They have telemetry, so they communicate the data back to headquarters, and that goes on the web, so you can see those data real time.
En términos de lo que sería datos de lluvia, barrio specific, la realidad del caso es que eso no está disponible. Si nosotros podemos, ¿verdad?, en la oficina proveer lo que sería el pronóstico de lluvia, y entre más a futuro, ¿verdad?, más incertidumbre hay, pero sí se le puede, si toda esa información en términos generales para Puerto Rico, para el sur de la isla, está disponible. Lo que sería el pronóstico, y eso es a través de nuestra página, que gustosamente se puede compartir.
Eva, just an idea that this is a great conversation for the Drought Learning Network. There may be a place for the Drought Network to have all the links to the different pages, and that way we can interconnect all this information for everyone that's interested.
Thank you, Luis. That's a great point. Okay, we have a question from Jason Budzan. Sorry if I didn't pronounce that correctly. Can the use of mulch and the creation of composting materials not only help with soil erosion, but help with food security? Any comments from our panelists?
Well, I would add that it would also help with evapotranspiration losses. You know, mulch retards the loss of soil moisture due to evapotranspiration. So that provides more water, which helps with food security.
Perhaps this could be for Dave and Odalys. What opportunities exist for local communities to support drought monitoring?
Yo puedo empezar, por ejemplo, COCORAS es un programa de base comunitaria que se pueden dar pluviómetros a la comunidad. Ellos entonces monitorean lo que serían los totales de lluvia, porque 0 es un valor, saber si no ha llovido es importante. Así que eso sería una opción. De igual manera, precisamente a través del Climate Hub está para reportar los impactos asociados a la sequía, que de eso ustedes podrían, ¿verdad?, dar un poquito más de información, que sí hay oportunidades para los ciudadanos que puedan entonces ayudarnos precisamente a entender el detalle. Es lo que siempre menciono en todas las conferencias. Un déficit de lluvia de 3 pulgadas en el norte no es lo mismo que un déficit de 3 pulgadas en el sur de la isla. Así que los impactos son distintos, y si la gente del field, el que conoce la zona, nos puede proveer ese insumo, eso es muy bueno.
Thank you so much to all of our panelists for sharing your wonderful perspectives. We really appreciate learning from you and your expertise. This session has been recorded and will be available at a future date. Thank you all and have a wonderful afternoon. I hope you enjoy the conference.